This is problem number 10 from the textbook. It reads, compare the electric force holding the electron in orbit around the proton of the hydrogen atom with the gravitational force between the same electron and proton. What is the ratio of these forces? So when we look at the sketch that you're presented with, we've got an electric force being attracted to the nucleus because we've got a positively charged proton here and a negatively charged electron. That force can be written as F sub E, the electric force, which we can describe by Coulomb's law. K Q1 Q2 over the distance between those two, R squared. It could be D squared, that's fine. And we're going to relate this to the gravitational force between the same two particles, the electron and the proton. And those two, that gravitational force can be conveyed by big G times m1, m2 over r squared, because it's this distance that we're talking about, the radius of the electron in its circular orbit. The only thing that makes this a little bit easier is recognizing that r squared and r squared are, of course, the same numbers. They're the distance from the nucleus to the position of the electron. And so now that ratio can be written more simply as F sub E over F sub G, which is a ratio. We're expecting this to be fairly big, actually really huge, just because the electric force is so much stronger, which is going to be equal to K times the Q of the proton, which I'll remind myself by writing plus E, times Q of the electron minus E. And I'm going to divide that by big G times the mass of the proton times the mass of the electron. Both of those are fundamental and given to you on the inside cover of the textbook. So we end up getting 9 times 10 to the ninth. Our units are Newton meter squared over Coulomb squared. And then I'm going to multiply that by the charge of the proton, which is 1.6 times 10 to the negative 19 coulombs times the charge of the electron. Both of these, of course, the outcome from Millikan's oil drop experiment, 1.6 times 10 to the negative 19 coulombs. Now keep in mind that this is an attractive force. One of these charges, most notably the charge of the electron, is negative, but in this case we know it's attractive. And then we're going to divide that by big G, the gravitational constant, 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. And now we have to multiply it by the two masses, which you would need to look up. The mass of the electron is very, very small, about 1/1800th of the mass of a proton, and that becomes 9.11 times 10 to the minus 31 kilograms, really small, times the mass of the proton, which is 1.67 times 10 to the negative 27 kilograms. So when you run that through your calculator, you get a ratio of the electric force over the gravitational force, and that ends up being a really large number, 2.3 times 10 to the 39. And since it's a ratio, it has no units. And we can see, in this case, evidence for, kind of ranking the fundamental forces, the electric force being so much stronger, Sarah Chow, than the gravitational force.